Imagine stepping into a gleaming machine, the doors hiss shut, and with a sequence of blips and bloops, you are whisked away to another era, perhaps to the roaring 1920s or a distant, unfathomable future. The allure of time travel has permeated our collective imagination, bridging the gap between fantastical science fiction and the rigorous laws of physics. Yet, despite its prominent place in literature and film, the science underpinning time travel remains bound by insurmountable theoretical constraints and unanswered questions. This essay delves into the complex interplay between the imaginative world of science fiction and the empirical universe of scientific fact, exploring how far we have come and how far we might yet go. Time travel captivates us with its infinite possibilities, yet remains a concept more at home in the pages of a novel than within the walls of a science lab. While theoretical physics provides some breadcrumbs, leading to the notion that time travel could be feasible under certain extreme conditions, substantial gaps between these theories and their practical application remain. This essay explores these gaps, distinguishing hopeful fiction from the harsher realities of science. Albert Einstein's theories of special and general relativity provide the most significant scientific basis for the concept of time travel. Special relativity introduced us to time dilation, where time appears to slow down or speed up depending on the relative speed of objects in motion. General relativity takes it further, suggesting that massive objects warp space-time itself, potentially allowing for phenomena akin to time travel under extreme gravitational forces. However, the practical application of these theories to actual time travel presents monumental challenges, primarily due to the immense energies and exotic conditions required. Wormholes, or Einstein-Rosen bridges, are theoretical passages through space-time that could, in theory, connect distant parts of the universe or different times. These remain a popular device in science fiction, offering a convenient method for journeying through the cosmos instantaneously. In scientific terms, however, the creation and stabilization of a wormhole require conditions and materials that are currently beyond our reach, such as negative energy densities and extreme gravitational forces, placing real-world wormholes firmly in the realm of theoretical physics. Cosmic strings are hypothesized topological defects in the fabric of space-time, remnants of the early universe that could, under the right conditions, allow for time travel. If two such strings were to come close enough, they might warp space-time sufficiently to form a closed time-like curve, theoretically enabling time travel. Despite their intriguing potential, cosmic strings have not been observed, and their existence remains speculative, dependent on conditions that are not currently verifiable. Quantum mechanics introduces concepts that challenge our classical understanding of time. Quantum entanglement, for example, suggests a spooky action at a distance, where entangled particles affect each other instantaneously over vast distances, potentially implicating a form of temporal manipulation. Furthermore, experiments involving photons suggest the possibility of retrocausality, where an effect precedes its cause. These phenomena, while groundbreaking, do not yet provide a method to manipulate time on a human scale or allow for what would traditionally be considered time travel. The possibility of time travel raises profound philosophical and ethical questions. If one could travel back in time, could history be altered? And what would be the implications of such changes? The grandfather paradox, where a time traveler could theoretically prevent their own existence, presents a logical conundrum. These dilemmas extend into the realm of determinism and free will, challenging our conventional understanding of cause and effect, and raising significant ethical considerations regarding the use of such powerful technology. The technological hurdles to achieving time travel are immense. The energy required to warp space-time, as suggested by general relativity, or to stabilize a wormhole, is on a scale far beyond our current capabilities. Moreover, the engineering challenges, such as creating materials with negative energy densities or managing the immense forces involved, remain unsolved. Even if theoretically possible, the risks and unintended consequences of tampering with time could be catastrophic, raising practical and safety concerns that are currently insurmountable. Science fiction has long used time travel to explore themes of change, destiny, and power. In stories, time machines are often depicted as vehicles that can be piloted with precision to specific moments in history. In reality, scientific theory suggests that if time travel were possible, it would be far more chaotic and unpredictable. Science fiction often glosses over the profound implications and theoretical complexities involved, influencing public perception and understanding of what is scientifically plausible. While practical time travel remains elusive, certain experiments offer insights into the properties of time as predicted by relativity. Tests involving atomic clocks on fast-moving aircraft have confirmed time dilation effects, where time moves slower at higher speeds. Recent quantum experiments also explore the potential for particles to influence past states, hinting at a form of temporal manipulation. While these experiments validate some aspects of relativity and quantum mechanics, they do not suggest a mechanism for controlled or practical time travel. The mathematics of time travel involves complex solutions to Einstein's field equations, which describe how matter and energy interact with the curvature of spacetime. Some solutions suggest the existence of closed time-like curves, which could theoretically allow for time loops. The Gödel metric, another solution, suggests a universe where time loops are possible across the entire cosmos. However, these models remain mathematical speculations without experimental verification. Time travel theories, if proven, could revolutionize our understanding of the universe. They could potentially offer new perspectives on the Big Bang and the evolution of the cosmos, addressing unresolved issues like the horizon problem in cosmology. Furthermore, the implications for the laws of thermodynamics and information theory are profound, potentially leading to new physics that could accommodate time travel within existing frameworks. The study of time travel benefits from an interdisciplinary approach, incorporating insights from fields such as thermodynamics, information theory, and computational complexity. Philosophical and ethical perspectives are also crucial, as they frame the broader implications of time travel. This interdisciplinary inquiry not only enriches the scientific study, but also ensures a more comprehensive understanding of the potential impacts and responsibilities associated with such powerful technologies. Looking forward, the study of time travel remains a fertile ground for theoretical exploration. Advances in quantum computing, space-time research, and energy technologies may provide new tools to tackle the formidable challenges that time travel presents. Moreover, global collaboration in these research efforts can accelerate discoveries and help manage the ethical and practical risks associated with time travel technologies. Effectively communicating the complexities of time travel to the public is crucial in setting realistic expectations and fostering informed discourse. The sensationalism often associated with time travel in media and pop culture needs to be balanced with clear, accurate, scientific explanations. This not only educates, but also inspires a deeper appreciation of the scientific process and its impact on our understanding of the universe. In conclusion, while the fascinating concept of time travel offers an intriguing field of theoretical study, significant scientific, technical, and ethical challenges remain.